Hello friends, in this video I will talk about Large Hadron Collider, which is also known as LHC. It is situated at CERN, Geneva, Switzerland. So LHC stands for Large Hadron Collider, which, as I mentioned, it is situated at CERN, Geneva, Switzerland. So L stands for large because it has the large size, and the circumference is around 27 kilometer. So it is in the form of circular ring, so we have a circumference of around 27 kilometer. And H stands for hadron, and hadron means baryon, meson. And then collider means it collides two beams circulating in opposite directions. So we have a collisions in the after the beam circulation in this ring. So there are four big experiments at the LHC. So we have this ring called as LHC. So we have four main collision points where beam collides. So there four major experiments are located, like Atlas. Alice is the one of the experiment. This is also known as a large ion collider experiment, and the other is Atlas. It is situated here, one of the collision point of the beams. And CMS, another collision point, it's also known as compact muon solenoid. And then LHCb, another collision point. So LHCb is means LHC beauty. So there are four collision points in the LHC rings. There four big experiments are located. Atlas are also known as point 1, Alice known as point 2, and then CMS known as point 4, and LHCV known as point 8. So this, as I mentioned, this big ring is known as LHC, Large Hadron Collider ring. And so we accelerate in this ring particle up to TeV energy. Since we know that the energy cannot be reached at the TeV level in a single ring, so we have multiple stages of acceleration. So we start initially from LINIAC, and then after LINIAC we send the beam to the booster, and there you can see at every step energy is increased. And then we send to proton synchrotron ring, and then after we send to SPS, super proton synchrotron, and then you can see the energy is typically of 450 GeV. Then after we inject this beam into the LHC ring, where the energy can be reached at 70 eV. Typically we have protons energy is typically 70 eV. And then the LHC parameters, since as I mentioned this whole is known as CERN accelerator complex, these are college experiments are located around 100 to 150 meter underground to avoid the cosmic background. So we have a counter clock to circulating beam in opposite direction, and then we have a collision points at CMS, LHCb, and Alice and Atlas. Since we have this big machine, so we have some parameters. So just to understand about it, let's go some of the points. So radio frequency cavities are extensively used in this design of the LHC, which basically used to get the required electric field profile. So we want to accelerate the particle at some different time. So then this radio frequency resonant cavities are used there. RF cavities, also known as also RF cavities. So beams are hadron or ions beams. Basically we collide most of the time proton collisions, proton lead, and lead collisions. So these are ions, basically proton, and then lead also ion. So since lead consists 82 PB208, this is the symbol of lead, and which consists 82 electrons and 208 nucleons, basically proton plus neutrons in the nucleus. So we have to remove 82 electrons. So these are stripped off at different steps to make a lead ion. So we remove 82 electrons at different steps of this accelerations, and finally we got in this ring lead ion. So since let's understand now, if we are colliding proton and with the proton, since we know the proton size is of the order of Fermi meter, which is basically 10 to the power minus 15 meter. So single proton, if you accelerate one proton from the one side, another proton from the another side, since size is typically Fermi meter, we cannot collide with this precision. So single proton we cannot accelerate, or we cannot collide. We can accelerate, but we cannot we can collide. The probability will be very less. So we collide the beam in the form of bunches. So we have this ring. So we have typically ellipsoidal type of bunches. So these are filled in this in the ring, and then the so you can see in this diagram, typically bunches looks like typically ellipsoid. So in the z direction, typically size is around 7 to approximately 7 centimeter. In the x and y direction, the sigma of the distribution, proton distribution, protons are filled in this bunch. So the spread around x and y direction is typically 16 micrometer approximately. In the z direction is around 7 centimeter. So bunches, we create these bunches of protons using the resonant cavities. We use the electric field, resonant electric field, to create these bunches, and then we fill these bunches in the form of in this ring, LHC ring, and then we collide them. Now LHC collisions, as I mentioned that protons, we first create the bunch of protons, as all in the case of ions also we do the same thing, we create the bunches of ions. But let's say in the case of protons, we have two bunches. From, let's say on the left we have I shown the protons red red circles, and you can see that one bunch, another bunch, and in a bunch on an average we have 10 to the power 12 to 10 to the power 13 protons, and we collide them nearly at the speed of light. So the main idea, let's understand it. If you have two glass balls, if you simply collide them, they will broke into the pieces, basically is smaller than the size of the ball. So similar idea is that we will collide a proton here, and we will collide them at very high energy. So we will expect some particle smaller than the proton, and basically we can study the properties of the particle inside the proton. So let's then understand the other aspects also. So since protons are in the bunches, so we have the bunches of protons, many bunches. So the bunches, so there's a gap between the bunches. So there's a spacing in terms of time, 25 nanoseconds. So that this is the spacing between the bunches typically, and the collision frequency is you can simply divide by 1 over this spacing, bunch spacing, typically 40 megahertz, and the distance between the two bunches is, you can simply, because it's speed almost traveling with the speed of light, then you can simply approximately you can calculate the distance between the two bunches. It comes about 7.5 meter, and you can also estimate the maximum number of bunches which we can fill in the ring. So then you can also do 27 kilometer and divided by the spacing between the two bunches, then it comes around 3600. So in general we have smaller bunches than the 3600 because of the limitations from the side of accelerator due to the space charge accumulation. And then let's define the concept of events. So since we are colliding these bunches, so it may be when we are colliding these bunches, one or more proton can collide in a single collision. So when one proton collide with the another proton, it is defined as as a single event. So one proton collision is defined as an event. Then the next thing which basically characterizes the events is the luminosity, which is basically used to estimate the number of events. So the event rate is proportional to the luminosity. Is So you can just see the event rate is defined as dn over dt, which is basically luminosity times of cross section of nucleon collisions. So event rate is proportional to the luminosity. If you increase the luminosity, you will have more events per unit time, and that means you are getting the more number of events. So luminosity of this accelerator is of the one of the important parameter is so it events per second. Basically, if you just want to collect the event per second, basically proton collision, then it depends on the luminosity. The main important factor for us is integrated luminosity. So basically it is luminosity over a time. uh, then the importance of luminosity. So since I already explained that if we want large number of events, you can see that event rate is proportional to the luminosity. We can get this by, because sigma is typically constant at an energy. It is the nucleon cross section at a particular energy at which we are colliding the beams. And then if you want the large number of events, then you have to increase the luminosity. So the for the you have to increase the luminosity. If you get the more number of events, very large number of events, you will get the more statistical precision in the physics results. And this previously we are colliding bunches when one beam comes like this, another beam comes like this in this collision system. Let's say here, so here two beams comes at an beam 1 and beam 2 comes at an angle of typically bunch crossing angle 285 microrad. So you can, one beam comes like this, another beam comes like right now. At this stage we collide like this. We have a crossing angle when we collide, so around 285 microrad. So this is so we got some luminosity. Let's understand it. If you are colliding these bunches head on, that means if you are just in this particular case, if you are colliding, then you have the maximum number of collisions, like you will get the large number of collisions basically. If you just tilt them, then the overlap will be smaller, and then you will get the small number of smaller events, collision events. So in this case you can see the overlap is when we are colliding in this scenario, then the overlap is only this portion in this case. So we get corresponding luminosity to that overlap. Collisions correspond to that overlap. But if we can maximize this overlap, let's say if it is overlap is very large, then we will get the maximum number of events due to the overlap. So this is this can be done by Crab cavity concept. So this cavity this is a new idea. It will used in the future upgrade in the so what it does, normally if you just have bunches which is basically ellipsoid, so it comes here before collision, like if it is in the same orientation, then we have a collision angle between the two bunches. If you, before collision, if you can flip the direction of this bunch, then also in this direction you can also flip this direction. In this way you can make the full overlap. That means you will get the full geometric overlap. That means you will get the maximum number of events. So this is still in the process, in the development. This technology this will be used in the future to further improve the luminosity. This way you can also get the increment in the luminosity. So this is still an option for the upgrade. People are working on it. So now, since we have a large luminosity, that means we have large number of events. Now we have to collect these number of events. So we have to make detector fast to collect these more data. So this requires the detector upgrades for all the four experiments to collect the large number of events. And this is all experiments are working for the future upgrade. And then if we have a large number of if we have large number of events, then we will get the more precise physics results. And in addition, it also opens the possibility of discovery of rare particles, for which we have a smaller production cross section, like Higgs is one of the particle which has a very less cross section. And we will expect to have a more rare discovery of the rare particles which has very small cross section. Okay, thank you.